In this video, we're going to look at weak base, strong acid titrations. And we're going to start out with the weak base. So the base is what's going to be in our Erlenmeyer flask. The acid is going to be our titrant. So we're going to start out with a basic pH and become more and more acidic as the reaction or as the titration proceeds. So quick little sketch, right? If this is my burette, and then my flask, which is horribly drawn. We can probably do slightly better than that. I'd like you to at least be able to figure out what it is. This is not better, but we'll deal with it. So in here, I have my weak base. And then the acid is my titrant. So when we look at our titration curve for this, this time we're going to have volume of acid added. Right? Our titration curve is always pH versus the volume of titrant added. In this case, my titrant is my acid. So the volume of acid added. It is a strong acid, so I'm just writing that as hydronium ions. And then because we're starting out with the base and we're adding acid to it, my pH is going to start out basic, so up here, and become more acidic as the reaction proceeds. My equivalence point is still going to be the point where the moles of base are equal to your moles of acid. So this is going to be number 3 here. Number 1 is going to be initial. Number 3. And then just like we did with our weak acids, everything between my initial and my equivalence point, I'm going to give that a 2. And then everything from my equivalence point on, I'm going to give that a 4. And I'm not including the equivalence points or initial. My highlighter kind of went over that equivalence point a little bit, and I didn't mean it to, but so this is my 4. So 3 is my equivalence point, right? My moles or millimoles, the way that we're going to do it, but of my weak base are going to be equal to my moles of my acid. And then again, because it's a weak base, strong acid neutralization reaction, right? At that equivalence point, the salt that I'm producing is actually going to be acidic. So my pH is actually going to be less than 7 at that equivalence point. Initially, I just have a weak base solution. So number 1, this is just a weak base. You would solve for your pH as you would for any weak base solution, right? You'd write your base dissociation equilibrium equation. You would use your Kb. You would set up an ice table. You would solve for your hydroxide ion concentration. In between number 1 and number 2, it's going to be a buffer solution. And then everything after my equivalence point is going to be excess strong acid. Right? We've neutralized all of my weak base at the equivalence point, and then we kept adding strong acid to it. So it's going to be excess strong acid after that equivalence point. At that equivalence point, right, we had said that my salt from a weak base strong acid solution is acidic, so my pH is acidic, and we want to add to this, it's a weak acid solution, right? And we would calculate the pH as you would for any weak acid solution, right? Your acid dissociation equilibrium equation, set it equal to Ka, right? Solve for X, and then X is your hydronium ion concentration. We could add a bit of that to this if we wanted. So you would use Ka, ice table, etc. If we go up here, use Kb, ice table, etc. So for this one, I actually kind of want you to work through it on your own initially, just using this information, right? Nothing here is new, right? We've calculated the pH for weak base solutions before. We know how to calculate the pH for buffers. We know how to calculate the pH for weak acid solutions. And we know how to calculate the pH for excess strong acid. So I'm going to just give you a problem. I'm going to ask you to pause, work through it on your own, and then come back and we'll work together on it. So our problem, we're going to have 30 milliliters of a 0.100 molar ammonia solution is titrated with 0.0500 molar hydrochloric acid. And our Kb for ammonia is 1.8 times 10 to the negative fifth. To calculate the pH, after the following additions, of our hydrochloric acid. So the first one, actually let's do 0. Let's do it initially. So 0 milliliters, 20, 60, and 80. All right, so please, again, hit pause, try to work through this on your own, and then when you're ready, come back. Okay, so I'm right away, I'm gonna just do some little calculations that I know that I'm gonna use. I know I'm gonna need my pKa. I know that I'm probably gonna have a buffer solution here, and our buffer solutions are going to, I wanna use our Henderson-Hasselbalch equation, which requires pKa. I'm also going to need the Ka because if one of these values is at my equivalence point, it's going to be a weak acid solution and I'm going to need that. So I'm going to calculate my Ka, my pKa, and then I'm also going to calculate my volume needed to reach the equivalence point. So all of those numbers I just want to do first so I can have them. So I'm going to get my Ka by dividing Kb into Kw. So Kw is 1.0 times 10 to the negative 14th. And I was about to write negative 14th. That's a 5, sorry. So and I get 5.6 times 10 to the negative 10 for my Ka, and then my pKa is going to be the negative log of that. And I get 9.26 for my pKa. I know that if I have 30 milliliters of a 0.100 millimole per milliliter ammonia solution, that I'm starting out with 3 millimoles of ammonia. I know at the equivalence point, I'm also then going to need 3 millimoles of my strong acid, and then when I divide that by its concentration, again, millimoles per milliliter, millimoles would cancel. And we're going to get 60 milliliters. And again, I just like to do that. I know now that this is my equivalence point. I know that I'm not given the half equivalence point, right? Halfway to my equivalence point would be 30 milliliters. I know that my pH is equal to my pKa at the half equivalence point. So if I was given 30, that would make that step a lot less work because I already have the answer to it, right? The answer would be right here if it was 30 milliliters. So it's just, to me, it's a quick step. You have to do this calculation anyway because we need this number for our change table. So like that one additional step can oftentimes save you some work down the line. So I just always like to do that even if I'm not asked for it. So now we can start actually answering our questions. So the first one, I've added 0 milliliters of my strong acid to my weak base. So I just have a weak base solution. So part A. Right, this is where we're going to write our base dissociation equilibrium equation. So ammonia plus water going to hydroxide ions plus my conjugate acid. And then you would set up the ice table. Because we've done so many of these, I'm going to kind of take some shortcuts. I'm not going to write my columns. I'm just going to go right to the expression. But you would have your initial concentration of ammonia, which if we go back up to our problem here, right, is 0.100. You would subtract x from that. You would add x to the other side. You would set that equal to Kb because we're doing a base equation, right? I'm producing hydroxide ions. I wrote my base dissociation equilibrium equation. So I'm just going to go right to this and skip the ice table. By all means, keep writing it if it helps you to be able to set this up properly. Because my Kb is small, right, my concentration of ammonia is actually 0.100 molar minus x, but we can ignore that minus x, right, because that Kb is small. I'm going to solve for x, which again is my hydroxide ion concentration, right? My base dissociation equilibrium equation produces hydroxide ions. I might have said that backwards. And I'm just double checking my math here. I'm solving for x. And I got that x is 0.0013 molar. And then remember, x is representing hydroxide ions. So I'm going to calculate my pOH and then subtract it from 14. And then also remember, right, just kind of keep your eye on the prize here, or what we're doing. We're starting out basic, right? Right now, all I'm doing is I'm trying to figure out the pH of this solution in my Erlenmeyer flask. So I know that my pH is going to be a basic pH. So if you just wrote down 2.87, right, if you didn't realize that this was pOH and not pH, or sorry, if you thought it was pH and not pOH, hopefully the fact that it's an acidic number, if it was pH, would trigger something that you did it incorrectly, right? We need our pH to be greater than 7. So you just always want to kind of think about your answers. So my pH is basic. I don't know for sure that it's correct, but if I wrote down a pH of 2.87, I know for sure that I'm wrong. So part B, we're now adding base to it, or sorry, we're adding acid to it, right? I've added strong acid to my weak base, so we're going to set up that neutralization table. I am going to calculate the amount of acid that I've added. So we've added 20 milliliters. My concentration of acid is 0.0500 molar. So I've added 1.00 millimoles of my strong acid. My neutralization equation, I have my weak base. I'm reacting it with my strong acid. We're producing water and ammonium ions. I started out with 3 millimoles of ammonia. Right, we calculated that number up here. I've added 1 millimole of my strong acid. Right, that was this number that we just calculated. And then remember, always subtract the smaller of the two reactants from both of the reactants, add it to the product side. And I have 2 millimoles of ammonia. My strong acid has been neutralized. And I have 1 millimole of ammonium ions. So what I have at this point is a buffer solution, right? I have a weak base, and then ammonium is its conjugate acid, so I have a buffer solution. So I'm going to convert both of those to concentrations by dividing through my total volume, and then I'm going to plug them into my Henderson-Hasselbalch equation. So as far as total volume goes, back up to my problem, we started out with 30 milliliters. I've added 20 milliliters to it. So I currently have a volume of 50 milliliters. And I'm just going to set them both up and then get my calculator out and solve them both after. I'm now going to plug those into my Henderson-Hasselbalch equation. So my pH is going to equal to my pKa, which we calculated up here to be 9.26. Plus the log of the base component over the acid component. And then again, please make sure you do that division first. And I got my pH to be 9.56. Part C, so we have 60 milliliters added. I know that is my equivalence point. We've already calculated the number of millimoles of base. We also know that that's the same number of millimoles of acid that I'm adding. I am going to write that neutralization reaction just so you can see what's going on and how we're saying this is a weak acid solution. So I do have ammonia. It's reacting with my strong acid. I'm producing water and then ammonium ions. And then this was 3 millimoles. At this point, we've added 3 millimoles of my acid. So again, always subtracting the smaller from both reactants. This time they're the same number. So both of those are going to 0. We then add it to the product side, and I have 3 millimoles of ammonia. So just kind of comparing C to B, just so you can see the difference, right? If I look at B, after I did that change table, what I have is I have 2 millimoles of ammonia and 1 millimole of ammonium ions, which is the conjugate acid of ammonia. So I do have a conjugate acid-base pair. I have an amount of both of those, so that makes that a buffer solution. When I look at this one, right, both of these are 0, so I don't have anything there, but I do have 3 millimoles of this weak acid. So I have a weak acid solution. So this is where we would write our acid dissociation equilibrium equation. So my ammonium ions plus water going to hydronium ions plus my conjugate base. And then you would set up your ice table. Just like I had done on part A, right? We would have an ice table here. I just jumped right to our expression. I'm going to do the same thing. If you need to make the ice table, please do. I just know that we've done that quite a few times, so I am going to jump right to that expression. I do, however, need my concentration, right? It's concentrations that get plugged into our expression, not the amount. So I do need to take that 3 millimoles and divide it by my total volume to get my concentration. So my ammonium ion concentration is going to be that 3 millimoles. I'm just going to rewrite it a little bit bigger so it's legible. And then my total volume at this point, going back up, we started out with 30 milliliters. I've added 60 milliliters to it, so we have 90 milliliters total. So 3 divided by 90. I have an ammonium ion concentration of 0.0333 molar. So if you were to make that ice table, right, this is the initial concentration that we would plug in here. You would subtract X from it, you would add X over here, and then you would set those equal to Ka, because this is a weak acid solution. So going back up, our Ka we've already calculated. It's 5.6 times 10 to the negative 10th. And then that's going to be equal to the concentration of this, which is X, multiplied by the concentration of this, which is X, so X squared, over the concentration of ammonium ions, which is 0.0333 minus X. But again, because my Ka is small, we can ignore that minus X. I'm going to solve for X, which is my hydronium ion concentration, right? Rewrote an acid dissociation equilibrium equation. So I'm just typing into my calculator here. And I got X to be 4.3 times 10 to the negative 6 molar. And I just want to double check that real quick. And I got the same thing. pH is going to be the negative log of that number. And I got 5.36. we did say, if we go back up, we said that we expected our pH to be less than 7 at the equivalence point. And we did get a pH that's less than 7. So we don't know for sure that it's right, but we know that it's not for sure wrong, right? And then one more part. I'm just going up to the question here. We're adding 80 milliliters of my acid. So I'm just determining the number of millimoles that we've added. So that's 4. And then I'm going to write my neutralization equation. So ammonia plus my strong acid going to water plus ammonium ions. I started out with 3 millimoles of ammonia. We've added 4 millimoles of my acid. Subtract the smaller of those two numbers, which is 3. Add it to the other side. So all of my weak base has been neutralized at this point. I do have 1 millimole of strong acid in excess. And then we also do have 3 millimoles of my weak acid. And just like with our weak acid strong base titrations, right, at the end we had excess base, and we said we were also getting hydroxide ions from the weak base that we had, but it was negligible compared to the amount that we were getting from that strong base. Same thing here, just reversed, right? This number, right, this is acidic. It does react with water to produce hydronium ions. We could write that acid dissociation equilibrium equation to get that value. We also have hydronium ions here. And the amount that we're going to get from this ionization is actually going to be negligible compared to this. So we are going to just ignore this number. So I have excess strong acid. We do need to turn that into concentration by dividing through by our total volume. So we started out with 30 milliliters of ammonia. We've added 80 milliliters of acid to it. So I have 110 milliliters total at this point. And I'm just typing this into my calculator. I get 0.00910 molar hydronium ions. And then my pH is just going to be the negative log of that number. And I get 2.04. So again, we were starting out basic, right? Because we're starting out with a weak base solution. We're adding acid to it, right? Acid is our titrant, and we're becoming more and more acidic as we go. At the equivalence point, right, I do have an acidic pH because the salt produced from my weak base strong acid neutralization reaction, right, the cation of that salt is acidic, right? It does react with water to produce hydronium ions.